In our current implementation, a much bigger problem than fragmentation is the time it takes to find a free block. So if we call malloc in a state where we've allocated a whole bunch of blocks previously, then we might have to look a long way to find this free block in the linked list of blocks. And that is why we're seeing our test programs run so slowly. The way to solve this is, instead of searching through all the blocks to find a free block, keep a separate list of just the free blocks. And if we do that, that's called having an explicit free list. The implementation we have now has an implicit free list. It's implicit because it's mixed in with the list of all blocks. You just have to look in there and pick out the ones that are free to implicitly get the free list. But if we explicitly represent the free list, we don't have to sort through the allocated ones. How do you represent this free list, though? We don't want to allocate separate data structures because that requires allocation, and we're implementing the allocator. What we can do instead is, since the free list is only relevant for unallocated blocks are the ones where the allocator is allowed to write inside of them. So we can overlay this linked list structure for the free list over the blocks in their unallocated form. In other words, for every unallocated block, we can just use its first word to put a pointer to make a linked list. We'll need a static variable or global variable that's private to our allocator called free list to keep track of the free list. And here you see we're in a state where there are 4 blocks that are allocated. There are 2 blocks that are unallocated. And we can find both of them by starting from the free list pointer, then following the next pointer down to one that doesn't have a next pointer that's nulled out to say that it's the end of the free list. Right, so a typical linked list just embedded inside of our overall array of blocks. In this situation, if the application frees the block P3 here, that means that we're going to set the 1 bit to 0 to say that it's free now, but also we need to add this block to the free list. And we can add a block to the front of the free list by first installing a pointer to the current head of the free list. So we're just copying the free list pointer into the first word of the unallocated block. Then we want to move the free list pointer to point over to this new block, and that way we have added this one to the front of the free list. If we're in this state now, suppose that this green block goes away. Then what happens? Well, we want to coalesce this green block with the one that's after it, but the one that's after it is currently in the free list. So when coalescing causes the next block to go away, we'll need to make sure it's out of the free list. So the first thing we'll do when we're about to deallocate this block is we will take the one that we're going to coalesce it with out of the free list. How do you take something out of a linked list? Well, you have to walk through the whole list. Maybe it would be more convenient to have a doubly linked list. Let's come back to that though. So the first thing we do is we take this one out of the free list. Then we coalesce, and in this case, the free block that we just freed gets coalesced with one before. So when that happens, then you don't add the newly freed block to the free list. So again, the effect of coalescing is, if you're going to coalesce with the block before, don't add the new one to the free list. If you're coalescing with the one after it, then first remove the one after from the free list. And what this does is maintain the invariant that every unallocated block is on the free list. It's on the free list exactly once, and there aren't other blocks that shouldn't be on the free list. If that linked list was not convenient, it's inconvenient to remove something from the middle of a linked list, you can always use a doubly linked list. Again, just overlaying it with the payload space that's not being used for an allocated block. Whatever data structure you want to overlay, you just have to make sure that when you malloc a new object, that you make sure that you use the maximum of the size that the application requested and the size that you will need when you are using it as an unallocated block. And then in a function like coalesce, where it wants to manipulate this overlaid data structure, you will just end up taking the payload pointer and casting it to your data structure to do something like call the add to free list function.